Lesson 2.9. What can we learn today? We're going to learn how to convert between exponential functions and their inverse. What we're going to learn today is called a logarithmic expression or a function. And we're going to learn how to graph points on a logarithmically scaled vertical axis, which you're going to see at the end is kind of neat. It's different. Certainly it's different, but it's kind of neat. We'll see that at the very end of class. So getting started here. Every operation in mathematics, if you want to solve something using algebra, you have to use opposite operations. Some of you are like, nah, I can just do insolve. True, if you have a calculator, but not everything in math are we allowed to insolve. So how do we solve using algebra? You have to know the inverse. For example, what's the inverse to addition?
Subtraction.
Subtraction. So right over here, if you want to write subtraction, where'd my pen go? There it is. Subtraction. And so what would that look like? It would look like this. If you were trying to solve for x, you would subtract 3 from both sides, and we'd have x equals 7 minus 3. Now, what is 7 minus 3? 4. And now we can state what x equals because we did the inverse operation. Or here, what's the opposite operation, the inverse operation of multiplication? Division. Let's go ahead and fill this in. Division. And so if I wanted to get x by itself, x isolated is the mathematical term, you would divide both sides by 3. And so we'd have x equals 7 divided by 3. Can that be reduced? No. 2 1/3, we'll leave it like that. Okay. Here's another one. What about if something was cubing?
You would take it to the third root.
You'd take it to a third root. Or you could call it third root. You can call it the cube root, whatever you want. But a root is like a fraction power. It does it's the inverse operation to a whole number power. So on this one, I would take a third root on both sides. Whoops. Let me, how about this? I'll just write x equals, I'll follow the pattern. X equals, and now I'll do a third root of 7. Now that would be asking you what number can multiply by itself 3 times to give you 7. Not multiply itself by 3, but multiply itself by itself 3 times. We don't have a value for that. 7's prime. So, and now here's a new word, exponentiation. What's the inverse of an exponent? That's a variable. Answer is a logarithm. So here's how a logarithm is going to work. What happens on this inverse is 7, technically as I walk through this, 7's by itself, it's going to represent the y. Here's your variable on the base. What's going to happen is you're going to have x equals, these two are basically going to switch places. The base is going to be written real small after the word log. You're going to write it down here. It's a subscript. That means down low. And what happens is the 7 and the x change places. This is where the inverse takes place, right in here. So it'll be log 3, 7. That's what the answer would look like. Again, you could type it in the calculator reduce. It will not be a whole number there. What a logarithm does solves the problem of 3 to what power equals 7. That's what a log does. It'll solve for what is the power. It solves for a power if you have an unknown power. Because we can't do a root if we don't know what the root should be. Let me differentiate here. On this one, we know we needed the third root. This one, we don't know what the power of x is. So we don't know what power to use to cancel it. So that's why you use a log. What happens are these two switch. So recently we learned about exponential functions and their properties. We would like to solve equations involving exponential functions, which creates the need for an inverse operation related to exponentiation. Okay, here's what I want you to write. Here, put a base raised to an exponent equals some number. Now, this right here is in the form of exponential. Maybe I should put exponential in the front so you can see that. Let me slide this over just slightly. That right there is exponential form. Exponential form. That's exponential form right there. So what happens with the logarithm, and I'll throw in a variable here. The exponent is an exponential form. That's your x, and the number itself represents the y. Since we're doing an inverse, it's those two that switch. And so in logarithmic form, it's going to look like this. And since I put the y on the right side, I'll do it again. You're going to have log with your base as the subscript. But instead of raising the base to the exponent, it's going to look like a base raised to the number. Now, after you write number, I want you to put x here. And that, in its entirety, will equal the exponent. And I want you to put y there. I'm sorry I ran you out of space. I got it about as tight as I could. But I want you to notice what changed places here. Here on the first one, exponential, it was a base raised to a exponent. Down the logarithm, it looks like a base raised to the number. Now, why did those switch? Because to find an inverse, what do you switch? X and y. So I switched what represented x, which was exponent, and number y. So the number became x, and the exponent became y. So that's how we use a logarithm, and that's how you can solve this without the use of, say, InSolve or Mathway or PhotoMath or whatever else you use. That's how you can do that by hand. So with that, let's just practice a few of these. So actually, sorry, take that back. Just as we can write rational numbers in decimal form or fractions, in fraction form, we can also write equations in exponential form. I got ahead of myself in the last slide, looks like. Exponential form or logarithmic form. Meaning two things can look different but have the same exact value. 0.5 is equal to 1/2. It says these forms create equivalent statements that express the same claim. We are not changing the problem when we convert back and forth. We are simply rewriting the equation in its equivalent form. So again, here it is shown this way. Notice what two letters switch places, which in this is represented by A and C. B, why did we use the letter B? What does that stand for? The base. The base does not change. Base does not change. And just to be clear on what the base is, I'll put here in parentheses, the base B does not change. It probably won't let me break that apart, but that's the B. It does not change. It'll always look like it has something being raised on it. Some things you're going to see here is that if you have a log without a base showing, it's a base of 10. Now, there's one more here that I was surprised did not come up in the AP classroom. We're going to add this here. A natural log. If you see ln, and I'll just use the number 3 again. If you see ln, that stands for natural log. That's when the base is e. ln3 is the same thing as log with a base of e raised to the 3 like that. Log base e of 3. That's how you read that. So natural log of 3 is the same thing as log e of 3. So I'm going to make a difference here. If you see ln, it will not show you a base. What's its base if you see ln? E. What if it says log, but you don't see a base? 10. That's called a common log. Common logarithm right there. That's log with a hidden base. This is a natural log. This is a natural logarithm. Try that again. There we go. Okay, now with all that, now we'll finally hit some examples here. All right, let's convert the following equations from exponential form to logarithmic form and simplify if possible. Okay, so this one, you might know the answer. 3 to what power equals 9? It would be 3 squared. Now, let's say you didn't know that. How could you solve it? You would change it to a logarithm. If I change this to a logarithm, what I would have is these two would switch locations. So I'd have log, what was my base? 3. These two switch locations, so it's log 3 equals x. Notice we've isolated the x. And if you wanted to check in your calculator, where's my calculator? If I check to my calculator, there's a log button that's, you press the control on the left side, press the control, and then you'll see log. It's 10 to the power of x button. When you press that, you can do log little base 3 of 9. Log 3 of 9 is 2. Notice that the answer is 2. What does x equal? X equals 2. So that's how you would do that without in solve. Okay, what about this one? How can we rewrite this?
Log base, say log and log y.
We'll simplify that in a second. So log base 10, these two switch places. Y equals x. Now this you could simplify and say that x equals. Can I type that part in the calculator? No, because it still has a variable, but I can simplify it. Instead of saying log 10, I can just say log y. And that would be my solution there. So if you have a base of 10, traditionally we don't write it. It's kind of like this. A square root, it's very similar. If you write a square root, what does this actually cancel? Does this cancel a power of 3? No, what does it actually cancel? A 2, but we don't actually write the 2 there, do we? But as soon as the power gets off of 2, if you wanted to cancel a third power, I would need to do a third root, and then you would include it. It's the same concept. Like on a root, you don't put the 2 if it's a square root, but everything else you would. Okay, what about the next one? I'll let you try this. What are you coming up with this time? What's the little subscript? R is the base in this case.
W.
Can we simplify that? So I'm gonna leave it as log RW. I'm just writing it this way, just to have the isolated variable first. Okay, and then what about here? Log, what's our base? E. Y equals 3x. So if I wrote this again, I could write 3x equals, instead of log E, what can I write instead? Natural log y. And then one more thing I'm going to do to simplify this. How could I isolate this x?
Divide by 3.
I divided both sides by 3. I now would have x equals natural log y all divided by 3. Don't divide just the y, you need to divide even the natural log. So natural log y divided by 3. All right, convert the following and then solve if or simplify if possible. 2 DOLs for you. All right, so now let's convert the following equations from log form to exponential form and simplify if possible. Okay, so if I'm converting from log, what is it that's going to be inverted? Which two values? The x and the y. The 9 represents the y here, so it's these two that are going to be inverted. So this means you'll drop the logarithm entirely. So you would say 7 to the 7 was the base. 7 to the power of 9 equals x. Okay, go ahead in your calculator, type that in. That's going to be a very large number.
Oh God. 40 million. Oh God.
What are y'all getting here?
All
All right, I better just type it in so I can get it all right. 40 million. Well, it disappeared on me. 353. 607. Wow, large number there. Okay, B. What exchange places this time? The x and y. So it'd be y equals 3 to the power of x. Can I simplify that? No. I have 2 variables. Can't simplify that. Simplify it as far as it goes. I'll have isolated variable y out front. That's fine. Okay, what about here? This doesn't even show me a base.
10 to the
10.
power of 2.
It's a 10. Very good. So this would be 10 to the power of 2 equals y. And do y'all know that math off the top of your head? What is 10 squared?
100.
100. Good. And finally, LNC equals 4. There's a hidden base in there.
E.
E, that's a natural log. So it's saying e to the power of 4 equals c. You might want to type that in the calculator. E is roughly 2.71. So 2.71 times 2.71 times 2.71. Wait, 4 point something? That's not right.
4.6.
Oh, 54.
Yeah, 4.
And I'm going to do approximately, because this is not going to be exact, 54.6. And that's rounded correctly?
Mhm.
All right. Which brings us to our next DOL. I'll let you convert these two and simplify if possible. All right, so says when a calculator is not available, oftentimes a logarithmic expression is easier to calculate by utilizing its equivalent exponential form. Here's some examples. Let's say this is non-calculator problem. Evaluate the following expressions without a calculator. So here's what I would do. This is a value we're looking for. In math, if you're looking for a variable, we usually give it the letter x. So I'm just going to put x here. Let's just say that equals x. If we're supposed to evaluate this, what this is saying, if you convert it like this will help your mind to process what is log base 2 of 8. Well, now I can convert it and say what is, or the question becomes, 2 to the power of x equals 8. 2 to what power equals 8? The answer is 3. Now, if you want a technique for doing this, whoops, x equals 3. There is a very simple algebraic technique to solve this. And it goes like this, in case you don't know that 2 cubed is 8. You take the larger number, which one's the larger number here?
8.
And you start dividing it, and I do upside down because we might have to divide it multiple times, by the base. Which one's the base? 2. 2 goes into 8 how many times? 4. Now, the reason I do upside down division is because you continue on this process until you get a value of 2. So can 2 go into 4? How many times? 2. Now you stop there. Now, technically, if you're like, what if I did it one more time? Well, I'll go through that way. Technically, you should start there. You're done because it's all 2s. But let's just say you screw up because every year, inevitably, students will screw up. Let's say you do it one more time. Can 2 go into 2? How many times? 1. Now, truthfully, here's what we're doing. What we're trying to do is find out what power this is. Now, what is the opposite? No, I don't want to say it that way. Here's what we're saying. To get to 8, I need to multiply the factors 2 times 2 times 1. 2 times 2 times 2 times 1. Sorry, 2 times 2 times 2 times 1. So if I write that out, how many 2's do I have? 3 cubed times 1. Now, what happens when you multiply by 1? It's the same thing. So do I even need to write that? No, and that's why I say you don't even have to go this extra step here. Technically, I would end like this. Once I get to my base of 2, I would stop like that and say, okay, this is 2 to what power? How many powers of 2 does it take to get to 8? 3. That's how you can do that by hand if it's more complex. Okay, what about this one? 5 to the x, let me put this equals x, sorry. 5 to the x equals 25. And so again, if you don't know, you could do upside down division. And what do you get here for x? X is going to equal 2. Now here, before we move on, how about this? Let's make it more complex. Let's just sneak in over here. Let's write this again, but put a 31 in front of your 25.
What?
So log 5, 31, 25. Let's say we wanted to do that. Because my guess is, before you walked in the room, if I would have given this, you wouldn't have had a clue what the answer is. But I want to do an upside down division. So how do you do an upside down division? I guess let's first rewrite this. You would say this is 5 to the power of x equals 25. And again, this is showing you how to do it in case this is non-calculator section. You take 3125 and you'd ask yourself, how many times can 5 go into that? Can 5 go into 3? Can it go into 31? 6 times with the remainder of 1. There's the 1. So now can 5 go into 12? So that carryover 1 begins at a 12. Can 5 go into 12? Twice. With how many left over? 2. Can 5 go into 25?
Yes.
How many times? That means 5 goes into 3125 625 times. All right, do it again. 5. Can 5 go into 6?
Yes.
1 time with a remainder of 1. Can 5 go into 12?
Yes.
How many times? Twice with the remainder of 2. Can 5 go into 25? 5 times. Do I stop there? No, because it's not a base of 5. You just try to get all 5. So can 5 go into 125? Can it go into 1? No. Can it go into 12? Twice with the remainder of 2. Can 5 go into 25? 5 times. Can 5 go into 25? 5 times. All right, count them up. 1, 2, 3, 4, 5. X would be 5 here. Actually, I shouldn't be saying x equals because I added the x. I should just say the answer is 5. I shouldn't put the x because we added the letter x. So on all these, let me get this better. Answer would be 2. This would be 3. I should take that away. That's the answer when you evaluate. If you're wondering why did I erase the x? Did the problem originally have an x?
No.
No. I'll just call this a C here. I'll put a C. What happened here? Mine's not moving forward. All right, here we go. Well, here comes C. Spoke too quick. All right. Does anybody off the top of their head know what log 232 would be? So I did hear one answer correctly. Let's find out. So what you would do is you'd say 2 to the power, 2 to some unknown power equals 32. So once I rewrite it, now I can say, okay, which is the larger number? And we start dividing by 2. 2 goes into 32 how many times? 16. 2 goes into 3 once, the remainder of 1. So 2 goes into 12 6 times. Okay, 16. Can 2 go into 16? How many times? 8. Can 2 go into 8? 2 go into 4? 2 times. How many 2's do you see there? That means this would equal 5. Two to the 5th would equal 32. Okay, what about this one? I don't even have a base. 10. So if I wanted to rewrite this, I'd be saying 10 to the x equals 100. Now you'll probably know the answer. The answer is going to be 2. But let's just show the work. 100 divided by 2. No, I messed that up. What should I divide by? 10. And you get 10. And I can stop whenever I have the same base. So that's saying 10 squared equals 100. All right, next one. So this one's saying 16 to what power? Equals 4. So we're going to do, what did I say before? Do I take this and divide by that? No, I said you take the bigger number, divide by smaller number. Okay, so 16 is going to get divided by 4. How many times can 4 go into 16? 4 times. So that means 16 is the same thing as, now here's what I'm substituting though. I'm not going to change this 4. I'm changing the 16. So now I'm going to say 4 squared to the power of x equals 4. I know it looks tricky. What did I do there? I took the 16, I replaced it with 4 squared. Okay. Well, do you remember what happens when you have a power raised to a power? Multiply. So it's 4 to the 2x equals 4 to the first. Now, why do I put this? I'm going to here introduce the 1-to-1 property. 1, 2, 1 property. It says this. Honestly, we've been doing it every time over here. It says that if you can rewrite something, so like for example here, I'll do it up here. If I can rewrite something as 2 to the x, and what do we find out that 32 is the same thing as? 2 to the 5th. And you see how these have the same property? I mean, the same base, I'm sorry. You see how they have the same base? 2 to the x equals 2 to the 5th. Well, every time y'all just took for granted, you just said, oh, that means the answer is 5. What the one-to-one property says, this time I'm not going to write it out. I'm just going to say one-to-one property. What the one-to-one property says is once you have the same base, you can eliminate the bases and set the powers equal to each other. And so here, x would equal 5. Okay, so jump down here. What I would do is I would say, do I have the same base?
Yeah.
So 2x equals 1, and you're just a step away from solving. How do I get x isolated? Divide by 2. And so our answer is actually 1/2. Do y'all want to check that in the calculator?
Yes.
Go for it. Log 16 of 4. Press enter. So if you remember, a fraction power is the same thing as a root. So when we could have thought it this way, instead of saying 16 to what power is 4, which the answer is 1/2. If you want to think about how do I make a 16 of 4, if you took the square root of 16, would that be 4? Is the square root of 16 4? Yes, a division power is the same thing as a root. What we're saying here in our answer is it's 16 raised to the first, but then a square root on it. And that is 4. Okay, last one here. Log 3(1). Which is the bigger number? Let's say 3 to the x equals 1. Let me slide this over just a bit. Okay, 3 to the x equals 1. Which one's the larger number? 3. Okay. Can 1 go into 3? Yes, 3 times. Can 1 go into 3?
Yes.
3 times. Can 1 go into 3? Am I getting into an infinite loop here?
Yes.
Okay, so somehow here this isn't going to work. There you go. The answer is anything to the power 0 is 1. If you don't know that, I'll explain it to you this way. I'll give you a great reason for it. Why is anything to the power 0 1? Here's why. If I write it out this way, 3 to the first divided by 3 to the first. We've learned about exponential rules. What do you do when you have the same base raised to powers being divided? You do what's called the quotient property. What do you do with the quotient property? You subtract exponents. So that'd be 3 to the first minus 3 to the first, which is the same thing as 3 to 0. But come back here. What is 3 divided by 3? 1. And that's the reason why mathematically, if you look at it, anything to the power of 0 is 1, because what you're doing is you're dividing by itself. Anything divided by itself is 1. So the answer here is 0. If you type that in the calculator, have you tried that yet?
Yes.
Log 3(1), did it say 0? Test it. Log base 3 1. Does it say 0? Yes, it does. All right, your turn. Evaluate these two without a calculator. All right, example 4. Now we're going to use a calculator to evaluate the following expressions, round to the nearest 10,000. I'll let you just type these in. You go ahead to your calculator, type all these in, and I'll get your answers from you in a moment. Okay. All right, so hopefully you got, is the answer the number 1, 5? No, that would just be pure multiplication. We're not doing that. We're raising it to a power. 2 to what power is 10? There you go. What about log 9? What's the base if it says log 9? Do I have to type in the 10? No, because the calculator knows that if you type in log 9, it assumes the base is 10. Notice it filled it in as soon as I hit enter. So it's 10 almost to the power of 1 would equal 9. Not quite, because 10 to the first would be 10. Okay. Do it again. Log base 7 of 32 of, 135. What am I looking at? Press enter. There's that answer. And finally, log 3 of 6125. There you go. Got our answers. Just going to paste this into the notes and we're going to move on. So with the calculator, it says round to the nearest 10,000th. Actually, maybe we better do that just for the practice of it. What does it mean to be a 10,000th? Well, let's determine that here. A 10,000th, if you were to write out the number 10,000, it would be 10 comma followed by 3 zeros. How many zeros are there total?
4.
So 10,000th means you need 4 decimals. So here I'm going to do approximately every time because we're rounding 2 to the 10th. I need 4 decimals, so 3.32. Now what do I do here? Do I do 19? Do I do 20? Do I do 18? What do I do here? 19. There we go. Okay, perfect. What about B? 9.5.4. Now, would it be a 2 or a 3 here?
2.
2. Okay. Here, 2.52. 0.8, I agree. 0.8. And then finally, 7.9374. All right. One useful purpose for logarithms is when dealing with exponential data. So what's the relationship between a logarithm and an exponential function? What's the relationship between logarithmic and exponential functions? They're inverses of one another. That's their relationship. They're the inverses of one another. So would they have the same shape? Absolutely. But if you think of exponential typically curving up from the x-axis, if it's growth, up from the x-axis towards infinity, now what's going to happen is instead of curving up from the x-axis, it's going to curve to the right from the y-axis. When you do an inverse, this isn't an inverse there. If you're like going, well, that doesn't look like, well, that's because I have to explain this. So here's the problem with exponentials. When you graph it, it can be very difficult if you're going to put a lot of points. So would you say this is a lot of points or very few points?
A lot.
There's a lot of points. It can be very difficult when things grow exponentially to see the difference between the early values. You see how, like if I ask you, what's this point here? You could tell me 80, but could you give me a very good Y? You see how it's very difficult because how close they are together? They're so close together. But here's what we can do. And so this is just saying the graph above shows the population. This is a population change from I think it's 1620. This would be 1620 here. That's 1640, 1680. I know it's confusing. That's the number of years since 1620. And it's telling you in particular from 1620 until this point, and really they could have gone further. Just in here, you can't even hardly tell a difference. But they did from 1620 to year 80 in here. They said you can't even hardly tell a difference in the population in these. Over here, here's what's happened. We've taken a log of the vertical axis. Now, what does that mean to take a log of the vertical axis? Well, instead of counting by 1 million, 2 million, 3 million, where there's huge gaps, we've changed it to 10 to the first, 10 to the second, 10 to the third, 10 to the fourth, because, do y'all know why? It's a whole lot easier to see. So the population was written this way. All of a sudden, you can start to tell, you see how you can distinguish the values more apart? So we take a log, that's what we call this, a logarithmic scale of the y-axis. The values are a whole lot easier to determine. Notice, does this look like an exponential function? Yes. Does it still look exponential once you do that, log?
Yes.
I would say no, not so much. It looks a lot more, it's not linear, but it's close to being a line in here. Does that make sense? What happens to your data makes it easier to determine. Okay, so there's the groundwork. Let's look at our example. It says here, Example 5. The population data all right, once you flip over. The population data of English Americans in the United States since 1620 is shown above. The population data for the years 1840, 1860, and 1880 are given below. Plot these additional data points on the graph above. Okay, so just to make sure we're clear, this first value here is not actually year 0. What's this year referred to right here? This is 1620. So 0 right here refers to 1620. So what would that make 20 be? Okay, and my board froze up on me. Let me try this again. There we go. 1640. That makes this. Okay, I'm not going to fill them all in. Let's jump. This is 1680. This is 1700. So if that's 1700, what is 180? 1800. And that would make 260 be 1880. So the ones I really need are 1840, 1800, 1820, 1840, 1860. Whoops. 1860 and 1880. Those are the ones I need. Okay, so the first plot we're going to do is 1840, approximately 17 million. So what is 17 million in terms of this year? So basically what I'm asking myself is 10 to what power equals, maybe we should do this down here. We're saying that 10 to what power equals 17,069,453. Now, how can I solve that? A logarithm. That's why we call it logarithmic scaled. So go to your logarithm. This would be the common log. So we're doing common log because the base is still 10. That doesn't change. Of 17,069. Don't type in the commas to your calculator. 453. This will get us our y value. And maybe I shouldn't use the letter x there. I'm going to change that to a y. That will give us our y value. So type in log of all that. Let's see what we get. Log, it's base of 10, so I don't have to type that in. 17,069. 453. What are y'all getting? Now that's the power. So we're gonna go look at 7.23. So that y value here, we already got this x. We said the x is 1840 is 220. So we're gonna say this is 220, and then would y'all say 7.23? All right, let's go plot that point. So as best I can, I'm going to use this little dotted line. This is 1840. We're going to go up this way. And 7.23, maybe right in there. So I'm going to say that's the point there. So there's our first point. 220, comma, 7.23. Okay, let's find the next one. What are we typing in the calculator this time? 31,443, 321. And you don't have to type in the 10 for the base. 31,443, 321. Are y'all getting about approximately 7.5? 7.50? Okay. So at 240, we'll have 7.50. I'll move these over to help me out. 240, and I need this to be up at 750. I don't know, about right there, maybe. Never close that parentheses. We'll say this is 240, comma 7.50. And then finally our last one. We'll take log of 50, 189, 209. Log 50. Leave the base blank. Log 50, 189. Was it 209?
Yeah.
189, 209. I'm getting 7.70.
Yeah.
So this is 260 years after 1620 and 7.70. Let's back up here and we'll plot this. And I'll go up a little bit more, maybe somewhere in there. Plot that point. Now I'll take these axes away so it's not so distracting there. And that would be our points. So that's how you can logarithmically scale an axis to make certain values more distinguishable from one another. Now, the graph will oftentimes try to help you out. So like there, I was using dotted lines, but here, I think on your, is this a DOL? Yeah, DOL, I want you to plot these. This is how it'll normally look. So I want you to look. This is again, you can, instead of, you're used to on an axis, maybe counting like 1, 2, 3, 4, 5. You see how the x-axis is counting?
Yeah.
Now the y-axis, usually we count the same way, but with logarithmically scaled, the reason they don't is because the values are exponential data and it's easier. It might look like 1, 10, 100, and 1,000. And it looks like it's not counting the same way. Doesn't it seem like it's skipping numbers way too fast? Like we go from 1 to 10 here, and then I go from 10 to 100. It looks like I'm counting by different amounts. But really how it's counting is like this. 10 is the same thing as 10 to what power? To 1. 100 is the same thing as 10 to the second. So really what I'm doing is I'm counting by powers. And 1,000 would be, now within that, when they graph, oftentimes you'll see the lines like this. What they're trying to help you do is, once you get from here to here, you're counting by ones. So this would be 2, 3, 4, 5, 6, 7, 8, 9, and then we're at 10. But after you get to 10, it no longer counts by ones. It now counts by tens. So now it'd be 20, 30, 40, 50, 60, 70, 80, 90, 100. Make sense? Once you get to 100, how's it going to count now? Count by 100. So this is 100. This makes this 200, 3, 4, 5, 6, 7, 8, 900, and finally 1,000. Okay, your last DOL, go ahead and plot these points on this grid.